Ordinary differential equations are used in science to describe the evolution in time of different quantities. For instance, they can be used in astronomy to describe the motion of planets, or in chemistry to describe the evolution of the concentration of chemicals in a chemical reactor. An ordinary differential equation is simply a relation between a function and its derivatives. It is supplemented by some boundary conditions, which in this chapter we will assume are initial conditions for the evolution in time. Let's now see three examples of differential equations. This is the ordinary differential equation that describes the evolution in time of a deposit that you make in a bank account. So m of t is the value of the deposit at time t. Okay, and this is giving you a relation between the derivative and the function itself. So it's a first order differential equation because it involves only the first derivative, and it is explicit because you have an explicit expression for the derivative in terms of the function itself. The boundary condition here is an initial condition, which is the initial amount you deposit in the account. A second example of ordinary differential equation is the equation that describes the evolution in time of the position of a nonlinear oscillator, which is called the van der Pol oscillator. This is the ordinary differential equation. X of t is the position of the oscillator at time t. This is the first derivative, so that's going to be the velocity, and this is the second derivative. Since the equation relates the position with the first and the second derivatives, is a second order differential equation. Second order differential equations need to be supplemented with two instead of one initial condition. The initial conditions will be the position of the oscillator at time zero and the momentum of the oscillator at time zero. Notice that the velocity and the momentum are the same because we're assuming that the mass is equal to 1. The momentum at time zero, which is going to be a non-constant p0. The third example is the system of Lorentz equations. Lorentz equations were used to describe an atmospheric system, and they are three first-order coupled differential equations. The first order because they involved the first derivative of these three quantities, xt, yt, and zt. It's coupled and nonlinear because zt depends on, for instance, the product of x and y, and then some additional term, b is a constant, such as r and sigma r as well. Since there are three different quantities, we have to specify three initial conditions: the position of x at time zero, the position of y at time zero, and the position of z at time zero. The Lorentz equations are interesting because they exhibit chaotic behavior. In contrast with the van der Pol oscillator, which in the long time limit exhibits a limit cycle, the asymptotic behavior of the trajectory described by x, y, and z is a strange object called a strange attractor, which is a fractal. The fractal actually has a dimension which is not integer, and in this case it has a dimension between 2 and 3.